forebrain and tried to give you some of the tough pieces that I had to struggle with over decades. And having solved those little problems, back to some of the details. If we look at our early embryo, with the sulcus lumitans coming up to the midbrain, when we get into the forebrain, the difficulty is in knowing where the sulcus lumitans continues. Does it continue at all in the first place, or does it? Which of several sulci does it represent? Because we have at different stages one or two sulci that create a problem. Now, the earlier stage, we had something like this, with the epithalamus, the dorsal thalamus, the ventral thalamus, and the hypothalamus. And so we have 1, 2, 3, 4 indentations in the wall of the third ventricle, two of which persist into the adult, and these two fuse as the ventral thalamic neurons move out to form certain parts of what becomes the adult thalamus. Unfortunately, for terminology, this migration of the ventral thalamic neurons does not contribute to the subthalamus. So in the adult, we have the terminology like the thalamus, the subthalamus, hypothalamus. And there's sort of a natural tendency to think that the ventral thalamus went into subthalamus. Whereas actually, the dorsal part of the hypothalamus cells migrate out to give the subthalamus and those callus. So I have to caution you on some of these are pseudo-synonyms that are not real synonyms. So if we grow this up to the next stage, we still have the epithalamus, thalamus, hypothalamus, and the roof plate, and here and the floor plate down here. And this now is epithalamus and thalamus and hypothalamus. With the migrations of the ventral thalamus right here, coming out to form the a capsule around the thalamus, the lateral reticular nucleus, and the zona incerta, and small pieces of the geniculus, the large cell portion of the medial and lateral geniculus that we have. The dorsal piece of hypothalamic migration, green here, goes out to form the subthalamic nucleus, between thalamus, zona incerta, and hypothalamus. Here is going to be lens shape piece of the subthalamus. And then cells are going to migrate out around the developing internal capsule telencephalic structures. Grow out the Mickey Mouse ears here, and Rose Raymond curl around and back. So we have the telencephalon coming around like so, hollow structure. Lateral ventricle here. And the site of fusion between the diencephalon and telencephalon, so the internal capsule form. The telencephalon is going to accept some of the hypothalamic cells that come out here to form the globus pallidus. To join in with the developing striatum, which is also telencephalic. And so the striatum and pallidum come to lie lateral to the internal capsule, which forms as these two structures seal together. And so we have a mixture of telencephalic, diencephalic, deep nuclei that get variously grouped together in various terminologies as the basal ganglia. It sort of has depended over the past 80 years or so since Peter Wilson discovered Wilson's disease and began to make diseases of the basal ganglia respectable. That basal ganglia have gone through an evolution of being telencephalic motor nuclei because they were so involved in Korea and Estonia and Africa and things like that with predominantly motor problems. To a whole host of combinations. You can take almost any combination type. You can find an author who has proposed it. You'll also find that most of them leave out major nuclei, like the red nucleus or substantia nigra, as they regard as sort of mesencephalic structures, hardly worth talking about. They'll all leave out the thalamus, because that's, quote, sensory. Quote. And most of them will leave out the amygdala. There's a great big nucleus in the temporal lobe, bigger than the globus pallidus, with a much more complicated structure. So that's sort of the reason why I've eliminated the words basal ganglia. I found it useless in conversation, except to preface my remarks by saying, well, you or we may talk about basal ganglia, but which ones do you want to talk about? And of course, one of the most motorish of all of them was the subthalamic nucleus of diencephalic origin, which was destroyed by hemivalism, a great big wild clinging movements that became another little problem in terminology. Well, anyway, the migration of these neurons has posed a problem. not only in the concept of basic ganglia, but also in the concept of what the forebrain really is. If we draw the sulcus limites to a close, all of the forebrain becomes association plates, which is very close to the truth. There are very small parts of it that are not predominantly inner neurons. For example, the olfactory bulb is already going to be second for the neuron. The primary ones are out in the olfactory pathway, and those are made from the dosa. So the central protrusion is secondary neurons, essentially association plate, right, structure. The diencephalic protrusion, optic, does have the whole retinal structure as brain, but the connections beyond the rods and cones to the primary sensory receptors are already second, third order neurons, and complicatedly interconnected. So that even though those two are essentially purely sensory inputs, they very quickly become complicated, much like the rest of the association plate elsewhere. The only really motor component in the real sense of the word of something being secreted to do something somewhere would be the hypothalamus and the post-pituitary, and hormones are secreted there and released from there. They go really quite long distances. So the synaptic junction is maybe many hundred meters long. And the descending connections of diencephalon and telencephalon are essentially interneuron systems, like associated plate. So, some years I give the course doing it that way, stopping at this point, and make the whole forebrain association tight. Some years I pick one of these sulci and say, well, make that the sulcus limites configuration. This year I'm probably going to stop at that point and make the whole system of forebrain, diencephalon, telencephalon, association plate. Because we don't have any really motor elements at all comparable to the word sounds, segments. We don't have any real sensory plate elements comparable to neuropress elements. So, the diencephalon is a third ventricular structure, and the telencephalon lateral structure that, as mentioned, protrudes out laterally, bulges forward and posteriorly, with the junction point here as the telencephalon bends back as the great transverse fissure. Transverse, when looked at, say, from behind, if you're looking at it from this direction, you would see the two telencephalic Mickey Mouse ears bending back at a very acute angle going across the up to and eventually across the midline. It's almost a straight line. Transverse direction. And then that adhesion forms so that the thalamus, which is essentially diencephalic, comes to have a secondary relation to the floor of the lateral ventricle. these cues across here, so the thalamus, which came from the third ventricle, now has acquired a relationship with the lateral ventricle. And it was that fusion that I was talking about briefly yesterday in relation to that peripheral ventricular cyst that was in the right lateral ventricle and obstructing the posterior body and occipital temporal horn, but lined with very thick layer of collagen. And the question came, where does that collagen come from? And of course it could have come from the choroid plexus, which is the only really intraventricular structure. But it could also have come from the connective tissue that didn't quite get extruded as this adhesion was forming. And not infrequently, if you look in the adult thalamus, the region just below the ependema of the lateral ventricle, you can find a layer of collagen, which of course you don't expect to see, because you expect to see it all extruded. Just as you don't expect to see a piece of skin epithelium falling down and becoming an epidermoid cyst in the internal capsule, or early tumor. That is sort of an exaggeration of something happening accidentally and being included in this adhesive process. So as that piece of mesenchyme that I was postulating had pushed up into the lateral ventricle and was essentially collagenous, but that's pure hypothesis at the moment. It just happened to fit the day before's and today's subject matter. So any problem at this point on the general organization of diencephalon and pseudocephalon?
You said that the two questions. One, that is it all the globus pallidus comes from that dorsal epithalamic branch?
As far as I know. Mm-hmm.
Okay. And the other thing was that you're talking about like the large cell groupings, like in lateral geniculate. Does that also include cells?
As far as I know, and I haven't seen any comments on it for decades, it's the large cell, the bottom two layers of the lateral geniculate.
Mm-hmm.
I'm not sure where the large cells are in the medial geniculate.
But it doesn't feel needed.
But there are a relatively small number of cells that are supposed to come from ventral, embryonic ventral bones. You asked about the globus pallidus, and at this point, let me just point out that as these cells are migrating out, they leave their tails, axons behind, that grow in the other direction. And so one of the major outputs of globus pallidus is pallidophytothalamic. And another major output is going to be pallidothalamic. So these fibers are going across horizontally. The internal capsular fibers are coming down as the genes are getting bigger and bigger. They're coming down vertically. And so we have the two systems at right angles to each other, the pallidothalamic fibers and the internal capsular fibers coming down. And you can see what might happen, what does happen. They intersect. So that some of the pallidothalamic fibers end up going straight across. Pallidothalamic. The thalamic vesiculus, I think it's called in the adult. Or some get pushed around the internal capsule as the ansa, ventricularis that are coming, sweeping forward around between corpus pallidus and thalamus. And so it's essentially a continuous system of fibers that are going pallidothalamic horizontally, being intersected or pushed forward by the descending corticothalamic, corticospinal, and so on, capsular fibers. Ray or Tommy?
So which fibers are getting pushed out of their path?
The ansa ventricularis, pallidothalamic fibers that are going to make a hook, a curve around the internal capsule. Those were the fibers, historically, that Muscle Myers cut early 40s for Parkinsonism and for the first time produced relief of the Parkinsonian tremor without producing animal-creature.
It's still kind of puzzling to me. If somebody's red hypothalamus just growing axons where the photosynthetic line, you see how the axons might get pushed out of the way. This whole cell bodies have gone over to the photosynthetic line, leaving their axons behind. That's a little bit puzzled how that axons.
Well, I fused two processes. Sorry about that. In general, as cells migrate, neurons migrate, they leave a trail. So you're not too surprised to find pallidothylamus. In addition, as things develop, they make other connections. And one of the other major connections is pallidothalamic, which so we say is sort of upstream in terms of diencephalic origin. But it just seemed an appropriate time to say that here you've got them moving outside of the diencephalon into the telencephalon. Of course, they don't jump across the mesenchyme, right? You have to fuse, and then you go across that line of fusion. So as this fusion occurs, they're moving out. So essentially all the cell bodies end up in the globus pallidus lateral to the internal capsule, leaving one trail back to hypothalamus and acquiring another trail connection, pallidothalamic straight across, and pallidothalamic that becomes increasingly distorted as more capsular fibers come down. And so we end up with two grossly definable systems, the ansa ventricularis,
Which goes to where?
pallidothalamic, and the thalamic vesiculus, two different names for the same system. It just goes through the internal capsule. And then my mnemonic, the zona incerta, is important only because it will define the fields of Forel. H2 and H1, whatever it is, which are just geographic names for myelinated fibers that are running in this region above or below or medial to the zona incerta. The zona incerta and the lateral reticular nucleus form a capsule around the adult thalamus, the bottom end of which, zona incerta, serves as a gross, microscopic level, division between fibers above and medial to it. So Forel's fields, as we'll see, will include these pallidothalamic fibers as they enter into the thalamus, as they go around the internal capsule, are running in the thalamus. But they'll also include a lot of other fibers that are coming up in the thalamus from below. It won't be a surprise to you that we have cerebellar pallidothalamic or spinal tridonothalamic coming into various parts of the thalamus. We've talked about this before. But they'll be running, since the fields of Forel are below the thalamus, they'll be running in different parts of Forel's field. So the only mystery that I can see about Forel's fields is why they've been treated so mysteriously and so magically they contain something very specific. The contents varies from front to back as to which system is coming through them. Okay. But the caudate putamen are unequal halves of the striatum, which become divided by internal capsular fibers. And I have trouble drawing that relationship at this stage of development. The striatum develops from a tissue very near the nervous foramen in terms of the development of the encephalon, basal part. And so as it grows back, the part that becomes adherent dorsally and is split off by the internal capsular fibers becomes the caudate. The putamen keeps being pushed off, separated by internal capsular fibers staying lateral to it. So the globus pallidus, putamen, caudate are three nuclei in the gross adult from two different embryologic sources, and one of them split same kinds of cells, basically the same kind of connections, striatal pallidus. The output side, just split by the internal capsule. That concept is going to become important as we grow this up to the adult pattern, because the striatum gets drawn out in that temporal lobe spiral, just as the hippocampus did, as we saw at the Trieste. So we'll be following that in another day or so as the striatum and hippocampal migration spirals around in the temporal lobe. So we'll see the tail of the caudate down in the roof of the temporal horn, just as we see the head of the caudate in the floor of the frontal horn, and the body of the caudate in the floor of the body of the ventral. And behind, as the tail continues, posterior behind the thalamus. So we've got a continuous, changing relationship of tissue that's going to be in the bottom, front floor, if you look at it from behind, and top floor, or roof, if you look at it from below. And it's just part of that adhesion process as they spiral around the diencephalon. And so one could look for tail of caudate down here, roughly in relation to the diencephalon, and the body of the caudate, body up here, and the tail beginning on the side, to the posterior down. Now I've left out one piece. As these Mickey Mouse ears grow back and around, they can't cover the diencephalon completely. The diencephalon pushes them out to the side. They get a spiral. And so we end up with a piece of diencephalon which is bare. It has neither third ventricular ependymon nor lateral ventricular. And so we'll see a piece between epithalamus and caudate that is covered by mesenchyme, not by ependymon. and that's going to be narrowest up here at Monroe's parameter. It's going to be right next to the midline, right next to the anterior roof of the third ventricle. You're going to get wider as you go back, and there's more separation between epithalamus and caudate. So the bare area of the thalamus, so-called, is the part of the floor of this subarachnoid space, cavum veli nervata. Let me see if I can draw that up quickly into the adult. Let's take a coronal cut. Like this. At the level, say, of here's the epithalamus, thalamus, hypothalamus, floor, the epithalamus, thalamus, hypothalamus, floor, the roof of the third ventricle, floor, so that the diencephalon, around something like that, with the thalamus, hypothalamus, epi, thalamus, hypothalamus. Essentially the same embryonic relationship. Now we want to put the telencephalon in place. And so we will have a fornix, side of the line, septum lucidum, and corpus callosum, and some chorioplexus, and some caudate, some ependymit of the lateral ventricle. So here's the lateral ventricle, and the third ventricle, and the bare area in here, where we don't have any ependymit between thalamus and telencephalon. So all this space in here, that floor in the commissure plate, as it developed backwards, and this subarachnoid space in here is mesenchymal. Mesenchymal has not been pushed out of the way, as it increasingly is so as the telencephalon moves back and the adherent to thalamus. Now we have the putamen, globus pallidus, colors here, with the internal capsule coming between them. And then we want to have some tail of caudate down here in the temporal horn ventricle. And now we can begin to throw in some more cortex. See the gyrus, retronal, and so on around. Over here we're going to have a little piece of claustrum, and a little piece of insular cortex. And around here, so we have some cortex. Insular cortex around here is temporal. And the rest of the temporal lobe is going to come in. And now we come down here to the hippocampal formation. I have to pay attention what I'm doing now. Dentate gyrus, hippocampus, parahippocampus. And the fornix coming out this way, off of hippocampus. And we want some choroid plexus. And some roof. So to the temporal horn down here, with the lateral ventricle. Then we just make this all adherent across here. So we've got the telencephalon sweeping around, becoming adherent to the diencephalon, with a slightly interclosed migration of hypothalamal cells. I guess to keep the subthalamus in here. And we better put some of the lateral reticular nucleus in here. So insert it like that. That gets most of the structures, I guess. Epithalamus, thalamus, hypothalamus, migrations of ventral thalamus into lateral reticular zone inserta, migrations of dorsal hypothalamus into subthalamus subthalamus. Adhesions of telencephalon around, so that we have the deep structures, caudate, head, body, and tail coming around in the temporal horn. Putamen split off from caudate by internal capsule. And in the third dimension, the capsular fibers going behind the lenticular nucleus, is triangular, lens-shaped nucleus, the combination of putamen and lobus pallidus. So we have a retrolenticular part of the internal capsule, coming around underneath a sublenticular part. So we're going to have 3 dimensions to keep track of. Not just this coronal plane, but the migrations of the telencephalon and the diencephalon have essentially maintained exactly the same relationships, except they become posterior and then inferior as we get temporal horn form. So here's caudate and caudate. And we're going to, and here is fornix, hippocampal migration. Those are going to be 2 major parallel migrations we want to keep track of and account for. We can cut it horizontally, and we can hope we can imagine at least where you would put these telencephalic structures around the diencephalon. Does anyone have trouble with that in the horizontal section? Try it. Here's going to be thalamus. So this is going to be thalamus on the other side. The third ventricle between. And now what? Well, Monroe's foramen is going to be up here at the front end of thalamus. So the head of caudate there. The lateral ventral immediately next to it. And if that's the case, we want to get the tail cutting. Back here, because there's a continuous structure back, down, and around. We've caught it here, and now we're cutting it here. This first cut, we have to cut it up here. Went forward, the head of the cutting, backwards, the tail of the cutting. As we go around, we catch it down there again. Fornix. We've got the fornix here, as it goes down. Behind Monroe's Freeman, in front of Monroe's Freeman, as we go into mammillary bodies, like towns. And we're going to cut it again as it comes around the temporal horn, like right here, and it's crossing fibers back here to the other side. The corpus callosum we're going to cut up front and back. Notice how we angle it here. And so we want a septum lucidum between the corpus callosum and the fornix system. And now we just have to put in some more little structures here. We want to put the putamen and the globus pallidus. Leave you some internal capsular room. But keeping the caudate, putamen, tailed caudate more or less in line. And now you can begin to see how the internal capsule is going to have an anterior part and a posterior part in relation to Monroe's foramen level. And the posterior part is going to have a retrolenticular portion as well as this sublenticular portion. It's all a continuation again of the same adhesion between telencephalon and diencephalon. You just see this in 3 dimensions. And then just to fill in, we have claustrum, insular cortex, temporal lobe, frontal lobe, cingulate gyrus, and frontal lobe, and so on. Temporal lobe back here, occipital. And back at the corpus callosum level, we're going to have the cortex, back in the cingulate gyrus, back in the occipital lobe, and so on. So I think if you can keep in mind the embryologic development, you tend not to lose sight of what should be present in the adult. Any questions?
If you were to draw the cavity septi interpositum there, it would be between the 2 thalami, posterior to the fornix and anterior.
It would be coming in below the corpus callosum, fornix, commissure, psalterium. There's a telencephalic on top. We're going to reconstruct the great transverse fissure. And so it's going to be below telencephalic structures and behind the fornix, behind Monroe's spring. And it's going to be a roof over the, a space over the roof of the third ventricle. The floor is going to be the chorial plexus, the roof of the third ventricle. And the roof is going to be the floor of the commissural plate, septum lucidum, fornix, corpus callosum system. So you come in here, and the reason the pineal which is a piece of the roof plate region that's developed partly the diencephalic. And so from above the pineal and below the salterium, this comes subarachnoid space over the roof of the third ventricle, below the fornicate.
And is that where the internal cerebral veins lie?
The internal cerebral veins, the straight sinus back here in the dura, veins of Galen, going to be below the splenium, above the pineal, either side of the pineal, and give rise to veins that come in to drain the choroid plexuses and the thalamus. Coming up here and branching out to give the vein to the striatum. So internal cerebral veins ought to be very close to the epithalamus here, I think.
They're right on top of it. That's why I was just asking if they were in that space. It's not important. I was just curious.
They ought to be attached to something. So they may well be in the space. I'm not exactly sure. I'm going to run right here in the junction between striatum, caudate, and thalamus. Draining thalamus and draining striatum. So the branch going up and a branch coming down. Okay, now let's consider each of these diencephalic structures individually. And let me draw this in the adult in a sagittal plane. Here is anterior commissure, optic chiasm, mammillary body, lamina terminalis, pituitary stalk, floor, third ventricle, aqueduct. Monroe's foramen with the fornix coming down, sliding into the hypothalamus and coming down here to the mammillary body. Monroe's foramen going out that way, leaving the roof of the third ventricle here, choroid plexus, and turning sharply around in the choroid plexus of the lateral ventricle. Now I've got to fill in the posterior commissure back here, and the aqueduct. And now we want to put in a pineal gland and a venular commissure, and suprapineal recess of the choroid plexus, third ventricle. And so here we have the sulcus here, and thalamus, and hypothalamus. And serving as the attachment of the roof of the third ventricle, we have the epithalamus. Which is this little piece here. Cut section. and consists of heavily myelinated fibers. So they stand out grossly as a nice white streak. And so sometimes known as epithalamic striae. Stria on one side. Containing fibers that are coming from Q-encephalon, entering into the epithalamic stria, coming around this angle at the nose frame level. Containing fibers that are coming from hypothalamus, from olfactory portions. Something like 13 or so different structures contribute this little tiny, less than a square millimeter cross section of fibers that are sweeping back to end in the habenula ganglion. And here the cells give rise to axons that come straight forward and bend back as the retroflex bundle bent back by the red nucleus really ought to put in some a piece of the midbrain here, pons down here, and continue on with the posterior hindbrain and the roof and the cliculi, the cerebellum, where that piece of crust goes that section. These fibers coming from either side and including fibers that cross in the habenula commissure come down and join in a very peculiar nucleus, or synapse in a very peculiar nucleus, a midline nucleus. They wrap around those cells of the interpeduncular nucleus, which then gives rise to cells that come up here into the tegmentum, the dorsal tegmental nucleus, or the reticular formation, which gives rise to fibers that go down the street somehow. Reticulous spinal.
I'm sorry, the input to the habenula ganglion was what?
The epithalamic stria, coming from telocephalic, diencephalic, including olfactory, deep nuclei, amygdaloid nucleus, striatum probably. Really a very broad contribution. Part of them come into the stria terminalis, from the amygdala. As I said, it must be an unusual structure that does not give rise to fibers to this region. So it's coming from a very broad source to a very narrow neck of the tunnel to the habenula ganglion. It is very, very prominent, heavily myelinated tract, as you can see coming across and biting off a little corner of the little nick from the dorsal lateral red nucleus system. Back. And then in this very strange relationship to a midline nucleus. And at this point, one has to have a certain degree of either imagination, Freudian or otherwise, to see that this system is now clasping this midline nucleus. And those with more primitive Freudian impulses, relate this to the primitive importance of copulation and the primitive importance of olfactory input for that function. Well, I leave it. I don't know. The evidence for that is I'll leave it as phylogenetic. I don't think there's any other evidence for it. But it's a funny system. Why it should be so prominent in such a very small area. You can see it with the naked eye, grossly. But the only function I've found for it is to serve as the attachment. The epithyme strata serves as an attachment to the cortic plexus of the roof of the third ventricle. And what usually happens when we cut the brain, a little nick in the knife cuts not completely through the cortic plexus and tears it. But when you look at it, the roof is gone. You see this nice white line of the epithyme strata. But you know that if you see that, did have roof of the cortic plexus containing roof of the third ventricle.
That was also known as the stria medullaris, or what's
Stria medullaris thalami, right. Medulated, that is myelinated, attached to the thalamus. So, in that thought, we'll stop.